Hello, we're going to take a look at an implicit differentiation problem here. The question is asking, find the slope of the tangent line of x cubed plus y cubed minus 6xy equals 0. That curve right there is actually known as the folium of Descartes. It's a special, kind of looks like a polar equation graph. Got some nice loops in it, called the folium of Descartes. But anyways, when I look at this, we see find the slope. Well, we as calculus people know, hey, I see slope, that means take the derivative, because the derivative will tell us the slope of an equation. Alright, so we want to take the derivative of this. But then we notice it's not solved for y. In fact, this equation we can't solve for y in a nice clean way. This leads to a little more difficulty with the derivative, and it leads us to the thing called implicit differentiation, because of the y cubed, the 6 times x times y. And I want us to get a little bit of an understanding of how this implicit works. So I want to take a step back to a more simpler equation. Let's just look at y equals 3x squared plus 2x to start with here. And to understand how implicit differentiation works, it helps to use really good notation on normal derivatives. In fact, Leibniz notation to be specific. So when I take the derivative of this function, y equals 3x squared plus 2x, well, you take the derivative to both sides. You take dx to both sides. Okay, here's something to keep in mind, is taking the derivative, the process of differentiation. It is an operation, okay? It's a pretty fancy, involved operation, but it's just as much an operation in math as multiplying, or maybe taking the square root, or taking the log. And notice, in math, whenever you do something to an equation, you have to do it to both sides. When I take the square root of a function, I take the square root of both sides. When I take the log of an equation, I take it to both sides. Differentiation is an operation, so I take it to both sides. And our symbol, our notation for taking derivative is that dx. That says take the derivative of this. And it means a little more than that, but in essence it means take the derivative of this. So when I do it to both sides, it keeps the equation in balance, you could say. On the left side, or actually, let's start with the right side. dx of 3x squared plus 2x. Well, we notice that we're taking it with respect to x, so x is what's taking the derivative, and we have our power rules, so we just apply that. So I have 6x plus 2. But on the left side, we often write maybe f prime of x, or y prime, something like that. But let's refrain from that prime notation and instead stick with the Leibniz. We would write dy dx. That notation is standing for a little change in y over a little change in x. It's saying the ratio of change in y to change of x. Or another way, it's as x changes, how does y change? The change in y with respect to x. So as x changes a little bit, how does y change? And in fact, how does it change? Well, we have an equation for it. So for every little change in x, y is changed by this equation of 6x plus 2. That's our derivative describing that ratio of change, which geometrically, graphically, is the slope of the equation. When I use Leibniz here, it's clear that dy dx equals 6x plus 2. Or when I take the derivative of y right here, I get that dy dx. Alright, now let's take a step back and look at our implicit differentiation equation. So I have x cubed plus y cubed minus 6xy equals 0. And notice in that other equation, I could take the derivative of the x's. I could use the power rule because the ddx matched up with the x squared, like those variables matched up. And I also took the derivative to both sides. So when I'm here taking the derivative, I go ddx of the left, ddx of the right. I do it to both sides. Okay, and what does that look like? That looks like ddx of x cubed. I'm going to go real step by step here. So like the derivative distributes over addition and subtraction. So it's minus then ddx of 6xy equals ddx of 0. So I have all these derivatives. Well, in this first one, because our variable which we're taking the derivative with respect to matches up with the variable of our function, it's just a normal power rule. Or in other words, this is saying that as x changes a little bit, this x cubed function goes to 3x squared. But now in this second one, we reach our first implicit differentiation. And in fact, it's a chain rule, okay? It's a chain rule. That's what implicit is. The answer to this is going to be 3y squared times dy dx. You can think of this as a chain rule because that y there, well, we're used to it being like y equals x squared plus 2. You know, something like that, an equation. Well, right here, I just have the y. But in a sense, you can think hidden inside that is another function. Maybe it's y equals x squared plus 2. So I have this function, x squared plus 2, inside the y right here, and it's getting cubed. So I have a function inside a function, like that. So it's the chain rule. So I take the derivative of the outside function, which is then 3y squared, evaluated at the inner function. The inner function is y. And then I multiply it by the derivative of the inner function. And the derivative of y is dy dx. Okay, because that's kind of thinking I have y, take the derivative of it. Well, I can't say much more than that is dy over dx. Okay, and then it's minus this derivative. Oh boy, this one now. Now here's the thing. This is a product rule because I have a function of x right here, and then this function y. That's two different functions with a constant multiple of 6 out front. So it's a product rule, so I have to go through that. I can pull out the 6 from it, okay, because that is a constant. Product rule, derivative of the first function times the second plus the first function times the derivative of the second. And what did we say the derivative of y is? Dy dx. And then that's great right there. On the other side of the equal sign, ddx of 0, derivative of constant, 0. All right, let me just simplify something before we talk about the next idea in solving our derivative. So I let that 6 distribute along with the negative. So I have negative 6y minus 6x dy dx equals 0. Okay, so think back to how we started this. When we found our derivative of that y equals 3x squared plus 2x, it was dy dx equals 6x plus 2. What equals 6x plus 2? dy dx. This is notation for the derivative is equal to. That dy dx is our notion of the derivative. It's our slope, our change in y over change in x. That means when I look at my equation over here, this dy dx stands for the derivative. That will give me the slope. Whatever that equals is the slope of the equation. So that means I need to solve this for dy dx. And this is algebra skills now, in that if I can get terms with only dy dx on the left, I can factor it out and then kind of solve for it. So anything with a dy dx is going to stay on the left side. They are the winners. They won the lottery and they get to stay on the left side. Okay, and then the losers are going to get kicked over to the right side. So I have 6y minus 3x squared. I did the 3x squared last just because, I don't know. I don't like to lead with a negative. Lead with your positive. It's a good life lesson. I always start with the best. All right, and then on the left side, algebra skills here, we are going to factor out a dy dx. So I have dy dx times 3y squared minus 6x equals 6y minus 3x squared. And notice we can divide both sides by 3y squared minus 6x. And voila, those cancel out, so I've solved for dy dx. So let's just write this one more time. I have 6y minus 3x squared over 3y squared minus 6x. So what does dy dx mean? It means the derivative. So the derivative is equal to that complicated looking function. The slope of the equation is equal to 6y minus 3x squared. This is our derivative. This is what we've been looking for. Okay, so once you solve for dy dx, and then the problem is asking for, though, at the point 4/3, 8/3, what's the slope? Slope of the tangent line. Well, hey, can we make this a little easier? Notice how there's a 3 I can factor out of the top and the bottom. So if I do that, I would then cancel them both, and my equation reduces down to y squared minus 2x like that. This will be a little easier to work with. Almost every time you do implicit differentiation, or I believe every time, you are going to have y's and x's in your equation. So you need both parts of the ordered pair in order to make it work. All right, so let's plug it in. 2 times y, 2 times 8/3, minus 4/3 squared, divided by the y squared, minus 2 times 4/3. All right, fractions are friends, so let's just do some fraction work here. Equals 16/3 minus square the top and the bottom. 16/9. 64/9 on the bottom. Square the top and the bottom. Minus 8/3. Fractions, let's see, you need common denominators to subtract them. So I'll multiply this by 3 and you get 48/9. On the bottom, I multiply this by 3, I get 24/9. Okay, let's combine. So 48 minus 16, 32/9, divided by 64 minus 24 is 40/9. Dividing by a fraction is same as multiplying by the reciprocal. So this is going to be times 9/40. 9's cancel out. 32/40. Boy, who said calculus is hard? It's just a bunch of middle school math, really, with all these fractions. Because now we get to reduce it. Divide by 8, you get 4/5. So what do you know? The slope of, or the tangent line to the folium of Descartes, that's the name of that line, at 4/3, 8/3 is 4/5. All right, I hope that gave you a little bit of understanding of how this implicit differentiation works. Maybe going back to the groundwork of using Leibniz notation on normal functions lets you see how dy dx is standing for the derivative. That's why you want to solve for it. And also why this then involves chain rule. And anytime you take the derivative of y, you're going to have a dy dx left over after the chain rule.